You stand at the edge of a hole in the ground, not a hole you can see across, a hole that swallows light. The lift cage hangs on steel cables thicker than your arm, and the wind that comes up from below smells of wet rock and ozone. You step inside. The cage drops. At 15 meters per second, your ears pop twice before the first minute ends. The walls streak past, rough, black, wet. The temperature climbs 1 degree for every 100 meters you descend. By the time you pass 1 kilometer, the air is 35 degrees Celsius and thick enough to taste. You are not a tourist. You are an engineer on a 3-kilometer journey to the face of the world's deepest gold mine. And nobody told you the most disturbing part. Not the heat, not the pressure, not the 90-minute ride into the dark. The most disturbing part is how quiet it gets when the cage stops, and you realize the entire weight of the planet is sitting above your skull. Welcome to Mponeng. 4 kilometers down, 600 tons of rock above every square meter of tunnel. And the shaft that got you there? It cost more than some countries' GDP to sink through solid rock. There is a number you need to understand before anything else. It is not the $5 billion. It is not the 4,220 meters of depth. It is the number 77. That is the natural rock temperature, in degrees Celsius at the bottom of the deepest planned level of Mponeng. 77 degrees. Water boils at 100. Your blood boils at 100. In between, there is only a thin margin of survival. The engineers who designed this shaft did not solve a logistics problem. They solved a physics problem that should have been impossible. Because at 4 kilometers, rock does not behave like rock. It behaves like a furnace with 1,000 atmospheres of pressure squeezing every seam. The first thing you notice when you ride the shaft is the concrete. It lines the walls in a perfect cylinder, 2 meters thick, poured in sections that interlock like vertebrae. Every ring is designed to withstand the hydrostatic pressure of groundwater that would burst a steel pipe at 200 atmospheres. But here is what nobody tells you about sinking a shaft through solid rock. You cannot dig a hole 4,000 meters deep by removing rock. You have to remove the stress. Every ton of rock you excavate releases strain that has been building for 3 billion years. The Witwatersrand Basin, where Mponeng sits, is the oldest gold deposit on Earth. The rock there is Precambrian, laid down before oxygen existed in the atmosphere. When you cut into it, it moves, it creaks, it shifts, and sometimes it explodes. If you have ever stood near a construction site and felt the ground shake when a pile driver hits bedrock, you have felt 1/10,000th of the energy stored in deep-level rock. At 3 kilometers, the stress is so intense that drilling into it can cause a rockburst, a spontaneous failure that throws fragments of solid stone at the speed of a rifle bullet. The South African mining industry records hundreds of these events every year. Some are small, some collapse the tunnel. So how do you sink a $5 billion shaft through rock that wants to kill you? The answer begins not with the shaft itself, but with the headgear that sits above it. At Mponeng, the headgear is a steel lattice that rises 60 meters above the surface. It looks like an oil derrick designed by someone who hates weight. Every beam is hollow. Every joint is pinned, not welded. The entire structure sways in the wind by design. Because the shaft below is not straight. It is not plumb. The Mponeng shaft follows the dip of the gold reef, which means it angles away from vertical at a gradient of about 22 degrees. The cage does not fall straight down. It slides along a plane, grinding against guide rails that have to be aligned to within millimeters over 3 kilometers of twisting rock. The lift cables alone weigh 40 tons. Each one is a braided steel rope 12 centimeters in diameter, wound from hundreds of individual wires. When the cage is at the bottom, the cable stretches by nearly 3 meters under its own weight. The engineers have to compensate for that stretch every time they lower a load. If they miscalculate by half a meter, the cage can overshoot the landing and crumple into the sump at the bottom of the shaft. That 3-meter stretch is not a measurement on a chart. It is a live variable that decides whether the cage lands or destroys itself against the sump. Engineers at Mponeng calibrate that every single drop because the margin is half a meter out of 3,000. If you want to keep descending into problems this close to the edge, subscribe so you do not miss what happens when the rock itself starts pushing back. And drop cable stretch in the comments, if just imagining that tolerance made you hold your breath. And that is just the vertical transportation. The shaft itself had to be excavated using a method called shaft sinking, a process so dangerous that it has its own fatality statistics. Here is how it works. You drill a pattern of holes into the bottom of the shaft, called the sump. The holes are 2 meters deep, arranged in concentric rings. You fill them with explosives. You evacuate everyone to a safety station 100 meters up the shaft. You fire the blast. There is a buffer of water at the bottom that absorbs the shock wave and suppresses the dust, but it does not stop the rock from flying. After the blast, you have to wait for the ventilation to clear the fumes. Then you descend again into a pit filled with shattered rock that could collapse at any moment, and you muck it out by hand or by machine, and you drill the next round. This happens 24 hours a day, 7 days a week, for years. The South Deep Shaft, which is the deepest single-drop shaft in the world at just under 3,000 meters, took nearly 7 years to sink. That is 7 years of continuous blasting, mucking, lining, and drilling. 7 years with no sunlight. 7 years of breathing diesel fumes and silica dust. But here is the part that changes everything. The shaft is not just a hole. It is a pressure vessel. At 2 kilometers, the water pressure in the surrounding rock is 200 atmospheres. That is enough to force water through concrete. The shaft lining has to be sealed with a double layer of waterproof membrane and grouted with cement injected at high pressure. If a single pinhole forms in that membrane, water will jet through it at a velocity that can cut through steel. There is a documented case from the 1990s at a mine in the Carltonville goldfield where a water burst flooded a shaft at a rate of 30,000 liters per minute. The miners had 70 seconds to get to the escape ladder. 3 people died. The shaft remained flooded for 18 months. So every millimeter of the Mponeng shaft lining is pressure tested before it is certified. The concrete is mixed with silica fume to fill microscopic gaps. The reinforcement bars are epoxy-coated to prevent corrosion from the acidic groundwater. And even then, the lining is inspected every month by teams that rappel down the shaft on ropes, checking for cracks with ultrasonic sensors. But the shaft is only the beginning. The real problem is what happens when you leave the shaft and walk into the tunnel. The haulage, as it is called, is a passage 2 meters wide and 3 meters high, cut through quartzite so hard that tungsten carbide drill bits wear out after a single shift. The floor is littered with gravel and water. Overhead, the ventilation ducts sag under their own weight. Every 40 meters, there is a refuge bay, a steel box with a sealed door, a supply of oxygen, and a telephone that connects to the surface. The walk to the working face can take 40 minutes. During that walk, you pass through heat that climbs steadily. At the shaft station, it is 30 degrees. At the first crosscut, it is 38. By the time you reach the face, the rock temperature is pushing 60. You have to understand what 60 degrees feels like on exposed skin. It does not feel hot. It feels like you are being cooked. The air is so humid that sweat does not evaporate. It pools in your boots, in your gloves, under your hard hat. After 10 minutes of physical work, your core temperature rises to the point where the safety officer has to order you to the cooling station. That cooling station is not air conditioning. It is a room where blocks of ice are stacked against the wall, melting into a pool of water that workers stand in, sometimes for an hour at a time, just to bring their body temperature down. And this is where the engineers made their leap. Because you cannot maintain production if the workers are overheating every 40 minutes. You need to cool the entire mine, not just a room, the entire kilometer of tunnel. The solution is called a chilled water system, and it is the largest of its kind in the world. At the surface, a refrigeration plant with a capacity of 30 megawatts cools water to 2 degrees Celsius. That water is pumped down the shaft through insulated pipes. At the bottom, the water passes through heat exchangers, some as long as a shipping container, that cool the air in the ventilation system. The cold air is forced down the tunnels at a velocity that would be considered a wind in a storm. It dries the sweat off your skin in seconds, which is dangerous in a different way. You lose track of how much fluid you have lost. But the system works. At the face of Mponeng, the temperature can be maintained at 28 degrees Celsius, even while the rock around it is burning at 77. That is a temperature differential of nearly 50 degrees, maintained across a wall of rock no thicker than a few meters. A temperature differential of nearly 50 degrees, held apart by a few meters of rock. That is not engineering. That is a controlled miracle happening 2 miles underground, every second of every day. If that kind of problem solving makes your brain itch for more, subscribe, because the next video is about a machine that drills through rock that is actively trying to crush it. And drop a comment. Tell me what number hits you hardest from that cooling system. The 30 megawatts, the 2-degree water, or the 50-degree difference. And here is the thing nobody tells you about that cooling system. It costs more to run than the entire electrical consumption of a small city. The pumps alone draw 15 megawatts. The chiller plant requires another 30. Every day, the mine consumes electricity equivalent to 10,000 homes, and it must run continuously. If it stops for even 4 hours, the tunnels heat up to lethal levels, and the entire shift has to be evacuated. That is the fragility at the heart of the deepest mine on Earth. A system so complex that a single power failure can trap kilometers of tunnel in a thermal trap. But the cooling is not the only battle. There is the air itself. At 4 kilometers, the air pressure is almost 50% higher than at sea level. That means your lungs take in more oxygen per breath. But it also means that any gas leak, methane from the rock, hydrogen from the battery charging stations, can reach explosive concentration in minutes. The ventilation system moves 500,000 cubic meters of air per hour through the mine. That is enough to inflate a stadium every 2 minutes. The air must travel from the surface, down the shaft, through the tunnels, across the working faces, and back up through the return airway. The total path length is nearly 15 kilometers, and it all depends on a single fan station at the surface. 8 meters in diameter, powered by a 2-megawatt motor, mounted on vibration isolators that weigh as much as a freight truck. If that fan stops, the air in the mine goes from breathable to lethal in under 10 minutes. There is a backup fan. It can come online in 30 seconds. But during those 30 seconds, the air stagnates. The heat rises. And at every face, the workers stop and listen. Because in a mine that deep, silence is the worst sound of all. Now consider the cost of that shaft. $5 billion if the title number is to be believed. But the verified data tells a different story. The South Deep shaft, one of the world's deepest single-drop shafts, cost just over $300 million. Mponeng's entire development, including the underground infrastructure, is estimated in the range of $1 to $2 billion. The $5 billion figure may be the total project cost for an entire mining complex, not just the shaft. Or it may be speculation. But even if it is, the point remains. Sinking a hole through 4 kilometers of solid rock requires an investment that exceeds the GDP of entire nations. And that investment is not just money. It is time. It is lives. Every kilometer of shaft sinking in South Africa's gold fields has a fatality rate measured in men per meter, not per kilometer. Per meter. The Robinson Deep Mine, which held the deepest shaft record for much of the 20th century, claimed the lives of over 3,000 miners during its operational life. That number is not from a disaster. That is the cumulative toll of rockbursts, cage failures, falls of ground, and heat stroke spread over 90 years. Mponeng is safer. Modern mining regulations, improved ventilation, and better ground support have reduced the fatality rate by a factor of 10. But safer, in a 4-kilometer deep gold mine, still means annual deaths. It means a memorial wall at the entrance. It means families who never see the man who left for the shift. And still they go down. Because the gold is there. The Witwatersrand Basin contains more than 40% of all the gold ever mined on Earth. The reef that Mponeng follows is one continuous sheet of rock, layered with microscopic particles of gold, extending for kilometers in every direction. At a grade of about 10 grams per ton, every ton of rock that reaches the surface contains about 1/3 of an ounce of gold. At current prices, that is about $700 per ton. The cost of extracting that ton, including the shaft sinking, the ventilation, the cooling, the labor, the explosives, the transport, is about $550. The margin is $150 per ton. Multiply that by 5,400 tons per day, and you get an operating profit of just under $800,000 per day. That is why the shaft exists. That is why engineers spend 7 years sinking a hole through rock that tries to kill them. Because beneath 4 kilometers of Precambrian quartzite, there is a sheet of metal worth more than the cost of all the concrete, steel, and human sweat required to reach it. But the shaft is not the end of the story. It is the beginning. Because once the shaft is sunk, the real work starts. The underground development, the kilometers of haulage, the ventilation raises, the ore passes, the refuge bays, the sumps, the pumping stations. That is where most of the cost lies. And that is where the next set of impossible physics problems begins. Stay with me, because the shallow part of the mine is only where the engineers learned their trade. The deep part, below 3 kilometers, is where they had to invent entirely new methods just to stay alive. The first lesson you learn as a shaft engineer is that rock is not solid. It is a composite of fractures, faults, and layers that slide against each other under stress. At a kilometer, Those fractures are invisible to the naked eye. At 2 kilometers, they weep water. At 3 kilometers, they burst. The geotechnical teams at Mponeng map every fault line in advance using seismic reflection surveys. They drill core samples from the shaft path and test them for compressive strength. But the rock always surprises you. There is a fault that runs through the Mponeng lease area, called the Ventersdorp Contact Reef, that dips at a steep angle and is filled with clay that has the consistency of toothpaste. When the shaft crossed that fault, the ground conditions changed so dramatically that the sinking crew had to stop and install a support system that had never been used at that depth. They drove steel arches into the sidewalls, pumped cement grout into the fault zone, and bolted the entire section with rock bolts 12 meters long. The work took 8 months. The shaft advanced a total of 60 meters. That is the rhythm of deep shaft sinking. Weeks of progress measured in meters, interrupted by months of problem solving. The schedule is not measured in days, but in millimeters per hour. The South Deep shaft, which reaches just under 3 kilometers, took 7 years. That is 255 days per kilometer, less than 4 meters per day. A man walking at a relaxed pace covers that distance in 3 seconds, and at the end of those 7 years, the shaft was not complete. It had to be commissioned. The hoists had to be tested. The ventilation had to be balanced. The cooling system had to be brought online. That commissioning phase took another 18 months. During that time, no gold was produced. Only cash was spent. The $300 million for the shaft was sunk, literally, into a hole that produced nothing until the day the first skip of ore was raised. But the engineers knew something that the accountants did not. The shaft was not the product. The shaft was the machine that enabled the product. And that machine, once built, would operate for 40 years. That is the mindset you need to understand when you look at a $5 billion hole in the ground. It is not a construction project. It is a generational investment. The engineers who designed the headgear will be retired by the time the shaft reaches its full depth. The miners who sink the first kilometer will never see the gold that comes from the last. That is the kind of patience most people never develop. Working for years toward a payoff you will not live to collect. If that resonates with you, subscribe to stay with this channel. We track the projects that outlast their builders. And tell me in the comments, what is the longest you have waited for something to pay off? Not in patience, in meters. And yet they go down. Because there is something about the act of sinking a shaft that transcends the economic calculation. It is the same impulse that drove the Romans to dig a tunnel through a mountain for 16 years. The same impulse that drove the Cornish miners to hang on ropes in the dark, drilling by candlelight. The vertical truth is this: we dig because the metal is there, but we stay because the depth becomes part of us. When you ride the cage back up from the bottom of Mponeng, you do not emerge the same person. Your body has absorbed the pressure change. Your ears ring. Your skin feels the cool air of the surface as if it were a foreign element. And you look at the people around you, the ones who never left the surface, and you realize they have no idea. They do not know what it sounds like when a rock burst hits 100 meters from you. A crack that is not a crack, but a concussion wave that slaps your chest and leaves you breathless. They do not know what it smells like after a blast. The bitter tang of ammonium nitrate mixed with the iron scent of shattered quartzite. They do not know that at the bottom of the shaft, the silence is the loudest thing you will ever hear. The $5 billion is just a number. The engineering is just a list of solutions to problems that should have been impossible. The real story of the world's deepest shaft is not about money or concrete or steel. It is about the men who ride the cage down every day, knowing that the rock above them is not a static barrier, but a dynamic system that is always trying to close. And they go anyway, because in a deep mine, the only direction that matters is down. The shaft exists because someone decided that the metal beneath their feet was worth the weight above their heads. And every day, they prove that decision was right. Now consider this. The deepest level at Mponeng is at 4,220 meters. But the engineers are already planning to go deeper. The seismic surveys show the gold reef continues below 4,500 meters. That means the shaft must be extended. The cooling system must be upgraded. The ventilation must be redesigned. And the men must ride the cage 1 minute farther into the dark. There is a term used by deep-level mining engineers. They call it the critical depth. It is the depth at which the natural rock temperature exceeds the temperature that can be maintained by any known cooling technology. For conventional ventilation systems, the critical depth is about 3,000 meters. For chilled water systems, it is about 4,000. Mponeng is already operating at the limit of the chilled water system. The next generation of cooling, called the ice slurry system, is designed to push the critical depth to 5,000 meters. It involves pumping crushed ice through pipes rather than cold water, because ice carries more cooling capacity per liter. The ice slurry system was tested at a mine near Carltonville in 2018. It worked, but it required a complete redesign of the surface refrigeration plant and the installation of a second shaft for the return slurry. That is the scale of the engineering at these depths. Every 300 meters of additional depth requires a major capital investment. Every kilometer requires a new technological leap. And the gold is still there, so the shaft will grow, the headgear will sway in the wind, the cage will drop, and the men will descend into a place where the light is artificial, the air is manufactured, and the rock is always pressing. You will ride that tunnel one day, not as a miner, as a passenger. The gold from Mponeng ends up in electronics, in jewelry, in the reserves of central banks. The metal in your phone, the ring on your finger, the bar in a vault. It all came from a place 4 kilometers deep, dug by people who trusted the shaft. So when you look at that hole in the ground, do not see the cost. See the commitment. $5 billion, 7 years, 255 days per kilometer, and a cage that never stops dropping. The deepest shaft on Earth is not a monument to engineering. It is a monument to will. And the next kilometer is already being planned.